All right, so good afternoon, and today we'll be starting the seventh live session of the NPTEL work, CH20 course. So last week, we were doing a problem where we had a wire uh, that was carrying some current, and that current was in all its entirety due to the resistance of the wire was producing thermal energy that was being dissipated as heat. So that is how we modeled that wire as as an object with a constant heat source, and then we obtained the temperature distribution, this one within the wire. So today what we'll be doing is a slightly more advanced solution of this problem. So that would be called, uh, that would be a spherical nuclear fuel element. And so let me tell you a bit about, you know, the nuclear fuel element. So, okay. So since it's a spherical element, since it is a spherical element, doesn't it? It looks like this, something like this. And this is the core and the outside of this material. Let's draw a center line so it would guide us while we make another circle over it. This way. So both of these are circles. Forgive me for being bad at drawing. And this is, so this part is called the aluminum cladding. Okay. And this is the core that is the fissionable material. The fissionable material. So inside this aluminum cladding, what you've got is the core of made of a fissionable material like uranium or thorium or whatever you might have. So what's happening here, the particles are colliding at a really high kinetic energies, and all of that is being transferred for producing a nuclear reaction so that different species are being formed and a lot of energy is produced due to a mass deficit. So we won't be going into the details of how that's happening. You can always read it on your own uh, when you're not in the session. So what we'll be doing, at the center of this core, the source, the kinetic energy would be the maximum. This would be the max. And as you go outside, the collisions would decrease because of being, further away from the center of the energy production unit. So, and that is why, as you move farther away from the center of this entire spherical core, your thermal energy generation value should be reducing. So that is why we'll be having this. Let's say that uh, the volumetric energy source can be approximated as, for example, let's call this is RF, the radius of the fissionable material, and this one can be called RC, that is the radius of the cladding, the aluminum cladding. So the source can then be approximated as, let's say, S naught, that is the value of the volumetric heat generation at the center, plus B, where B is a certain constant, divided by R by RF, times the square of everything. So you see, as R increases, the energy source decreases. So it's smallest at the center and maximum at the outside. So here, what you'll be having, forget about the physics that's happening inside the core and the cladding. So here there will be two parts, okay? The first part that you need to solve for is the core, that is the fissionable material, and the second part would be the aluminum cladding. I won't be writing everything right here. Aluminum cladding. So there are basically two temperature distributions that you need to solve for, 1 and 2. So in 2, Sn is identically 0. So you do not have any sort of source, any sort of thermal energy generation inside the cladding, but you have something non-zero inside the core. So you need to perform two energy balances over one in the core, like this, and the other within the aluminum cladding. Okay, so let me just draw this one. Maybe like this. This is one, and this would be, this is one, and the other one, which we just drew, would be 2. Okay. Perfect. So here we go. So we should start now. Okay, so the first thing that we start with is TF, the temperature distribution within the fissionable material, and this TF, for calculating this TF, what you do is let's say this is the core with a radius RF, and one. And let's call this radius R, and let's call this thickness as delta R. Okay, so this is our control volume. And what we can do here is the first thing that we write is, since the primary mechanism of energy transport is heat conduction here, since the system is in motion. So what you do is you'd write rate of heat conduction inside would be equal to QR, that is the rate of heat transfer per unit area, that is the flux, 4 pi QR double prime, let's call that R square at R. All right. And you could also probably write F here for clarifying that this Q double prime is concerned with the inside of the core. And rate of heat conduction outside would be Q double prime of F r plus del r would be equal to times 4 pi r plus del r squared at r plus del r, of course. So this would be equivalent to q double prime times 4 pi r plus uh, 4 pi r squared and at r plus del r. Okay. And the third term would be the rate of thermal energy produced within the CV. And this would be, let's call this S. Sn at something like R. Since delta R is small, that is the thickness of this spherical element is really small, we could just ignore the spatial variations in the volumetric energy generation rate across the width, across the thickness of this spherical element. So we could just write it as S naught times 1 plus B R over RF squared. Or you could, yeah, and you could simply keep it like this. And this is the volumetric energy generation rate. Now you need to multiply it with the volume. And what is the volume? It is 4 pi. Now, R squared del R. You can calculate this as 4 by 3 pi r plus del r cube, which would be the volume of a sphere with radius r plus del r minus r cube. So, and within the limits, delta r tends to 0. So this would be it. And okay, so finally, what you could write is N would be equal to the amount of thermal energy that is heat that enters the control volume would be equal to the amount that exits, that is from the outlet, plus energy or what you could do right this way is okay. So just a moment. So in plus generation would be equal to out, right? This sounds reasonable, right? So this would give us q double prime times 4 pi r squared at r plus Sn r times 4 pi r squared del r would be equal to q double prime 4 pi r squared at r plus del r. All right. So 4 pi r squared del r is equal to q double prime 4 pi, we can take it outside, r squared at r plus del r minus q double prime r squared at r. And now what you could do is cancel this 4 pi. Since 4 pi is obviously not 0, you could easily eliminate it from both the sides of the equation. And you already know S and R. So what you do, you bring everything to the right hand side, and let's keep S and R on the left hand side. So you could just write S and R would be equal to q double prime r squared r plus del r minus q double prime r squared r divided by delta r. And since our delta r tends to 0, so you could just apply this limit right here. And through the first principle of derivatives, this looks exactly what something would look when it would be differentiated with respect to r squared. Yes, so this is how it looks. Now, once you know this, you could always write q double prime r squared d by dr would be equal to s naught 1 plus b times r over rf squared. Okay. All right. So, and this would be responsible for TF. Now for TC, this is the set 2. There would be no energy generation. So only in would be equal to out. And an identical control volume analysis would yield that you'd be having something, let's call this F, that you'd be having something like of this form. QC double prime R squared would be equal to 0 because the energy generation is 0. Okay. And this gives you TC. So for TF, what you could do right away is that you integrate this equation. Q of double prime R squared would be equal to S naught times R plus BR cubed over 3RF squared plus C1. And this can further be written as QF double prime would be equal to S naught 1 over R plus BR over 3RF squared plus C1 over R squared. Okay, so I think we made a little mistake right here. So Sn was to be multiplied by R squared right here. Yes, yes, right. So Sn should right here R squared right here. Yes. So we made a little mistake right here. Okay. Anyway, so this problem can be incorporated really quick. So you could multiply R cubed by 3 plus, just let me erase this part and this part as well. Okay. And this would become, R to the power 4, and integrating it would be R to the power 5. Okay, this one. And divide everything by R squared, so you won't be getting this. But you'd be getting something R by some form R by 3 plus BR cubed over 5 RF squared plus C1 over R squared. Okay. So we could start our analysis right here. We'd say that at r equals 0, qf double prime is finite, right? But from this equation, r tends to 0 implies qf is close to infinity. So how to resolve this misunderstanding between the equation and yourself is that you make C1 identically equal to 0. This would ensure there is no 1 over r squared term in the flux expression, and at r tending to 0, really close to the center, qf double prime would always be finite. In fact, it would be 0. So using this boundary condition, or asymptotic condition, you can just simply write that r by 3 plus br cubed 5 rf squared. Okay. Now, just look at the interface. This is the core, and that is F, and this is the cladding, that is C. So at this interface, from here you've got Q double prime F, and from here you've got Q double prime C. So since the interface does not store any heat, okay, so you could say that if you take a really thin control volume right here, close to 0 thickness. So this is the fissionable material, and this one is the cladding. So you watch it right here. This is QF double prime, the flux in the fissionable material, and this one is QC double prime, the flux in the cladding. So since this control volume is not, storing any kind of heat, so heat cannot be stored. It's not storing any kind of thermal energy. You could always write QF double prime would be equal to QC double prime. And this is the second condition, the second boundary condition at R equals to RF. Okay. So this sounds good. Okay. Now, identically, we could also write this particular equation that is for TC. You could always write it as QC double prime. R squared would be equal to, let's call that C2 maybe. Yeah, let's call it C2. Okay. So QC double prime is equal to C2 over R squared. And at R equals to RF, we've got QF double prime would be equal to QC double prime, which implies, let's write the right-hand side first, C2 over RF squared would be equal to, QF can be written as this one, and write it like that. It's not RF by 3 plus BRF cubed over 5 RF squared. Yeah, this is how it looks. So this becomes RF by 3 plus BRF over 5, which is equal to S naught times RF, 5 plus 3B divided by 15. So C2 equals S naught RF cubed by 15 and 3B plus 5. So this is another equation that you might have to keep in mind. And here we go again. Okay, so QC double prime would be equal to C2 over R squared, where R belongs to RF and RC. And this is equal to S naught RF cubed over 15 times R squared. And the constant part is 3B plus 5. And QF you already have from here. So let's start off with QF double prime, which is equal to S naught R by 3 plus BR cubed over 5 RF squared. I hope there's no mistake right here. And so this part you can obviously write it as minus KF dTF over dr at certain R would be equal to S naught times R by 3 plus B by 5 RF squared R cubed. Solving it further, you could always get it something like dTF over dr would be equal to minus S naught over KF times R by 3 plus BR cubed over 5 R squared. And this is dF, of course, and integrate both sides with respect to R once more. So you'd be getting something like minus S naught over KF R. This would be RdR. So RdR integral would be R squared by 2, and 2 times 3 is 6. Plus R to the power 4 by 4, that is 4 by 20. 20 R squared plus C3. Let's call this C3. All right. Yes, so doing a really similar exercise for QC double prime, you could write it as, first let me mark it with green, probably with this color or purple. This is okay, so this is a rainbow color. This looks good actually. Yes, so we could always write KCDTC over TR would be equal to S naught times RF cubed over R squared, and you insert that 15 inside. 1 by 3 plus B by 5. So again, we got to integrate it with respect to R in the next moment. So you write it in the consolidated form. You write it something like Tc would be equal to S naught RF cubed over Kc, that is the thermal conductivity of the cladding, the aluminum cladding. And, integration of 1 over R squared, or let me undo this thing. I'll choose this colorful pen. So integration of 1 over R squared dr would be equal to minus 1 over R. You can see that. Okay, so this is effectively this B by 5. We could always have that outside minus 1 over R plus C4. Yeah. I guess this looks very good enough. So we can write it as S naught RF cubed over KC R. And this is 1 over 3 plus B over 5 plus C4. This is TC. Let me mark it right like this. Okay, so now we write the boundary conditions. One thing would be the interfacial continuity. So this side you have TF, this side you have TC. So TF should be equal to TC at R equals to RF, right? And suppose that this is RF and this is RC. And you can always measure the outside temperature using a thermocouple or some other device. So you could always have a Dirichlet boundary condition right at the surface of the cladding, the surface of the entire thing, the entire system. That is the cladding plus the core of the fissionable material. So here you can always have this part as well. Tc at R equals to Rc would be equal to T naught. Okay. So writing this would be a bit mathematically demanding because you can write it something like this. Let's see this one. Okay. Yeah. Let's use the lasso selection tool. We'll select everything instead of writing it again. So we copy this and we paste this. Yeah, great. TF is this, and so you write it TF at R equals to RF would be equal to minus S naught by KF RF squared by 6 plus Okay, so the rainbow was better. Or maybe we could use this darker color plus b by 20 rf squared. So that's rf to the power 4 and divide by rf to the power 2 rf squared would yield rf squared plus c3 is equal to tc at r equals to rf, which is equal to s naught times rf squared divided it by kc, and the usual 1 by 3 plus b by 5 plus c4. Okay, so from here, you could always define C3 as S naught by KF. Take RF squared as a commonality, right? 1 over 6 plus B over 20. It's not RF squared by KF. I guess I wrote everything correctly. And plus S naught by KC times RF squared, again, 1 over 3 plus B by 5 plus C4. And this thing becomes take RF squared as common. So you've got 1 by 6 KF plus 1 by 3 KC plus B by 20 KF plus B by 5 KC plus C4. So let's keep it like that. C3 is equal to this. And now we switch to the normal marker. So you have C3 already. And from this distribution right here, you can always write TC at R equals to RC would be equal to S naught times RF cubed over KC RC, 1 by 3 plus B by 5 plus C4, which is equal to T naught. So you can always write C naught, C4 would be equal to T naught minus S naught by KC, RF by RC, and RF squared is a common factor, right? 1 by 3 plus B by 5. Makes sense, right? Yeah. So using all this, you can always write something like TF is equal to minus S naught by KF, R squared by 6 plus B R to the power 4 by 20 RF squared. And C3 is S naught times RF squared. And all this, lots of stuff right here, KC plus 2KF plus pick out B by 5 from here. And we could write 1 by KC plus 1 over 4 KF. And C4, we just calculated it as minus S naught RF squared RF over KCRC times 1 by 3 plus B by 5. So this is how it looks. Yeah, so I guess that's it. And using an identical methodology, you could always have TC would be equal to S naught and C4 we had calculated right over here plus T naught minus S naught RF squared over KCRC. No, C4 is this, yes, this one. KC times RF over RC and 1 over 3 plus B over 5. So you see that we could have something common out of everything right here, plus S naught times, just keep this as a common factor, times 1 over 3 plus B over 5. And here you'd have RF. You could always have RF cube as the entire, or RF over R minus RF over RC. So this becomes further, you could always write it something like this, RF cube over KC times 1 over 3 plus B over 5. And maybe you could also have, RC, RC right here, 1 over RC here, and you could write it as RC over R minus 1. Not bad, right? And you could always put R equals to RC to observe that this entire thing becomes 0, and what you're left with is T naught. So it also satisfies the original boundary condition that we took. So TC is this. Excuse me again. Some fault right here. Okay. So now that we have done something that we considered to be essential, because there are several instances where you have a variable heat source within your solution domain. So how to handle that, we just checked it out. And further now, we'd be discussing the integral formulation for the boundary layer. So while I do not think that we need to go into the fundamentals of what is a boundary layer and how it is formed and its evidence and all, So we'd assume that you already know what is a boundary layer. And so what we'll do is that we'll go straight to the equation, assuming that you all know what a boundary layer is. And once you know that part, we'd yes, so we just start with the integration. So okay. Okay, so we'd go with the simple case, and maybe in some other time we'd take up the complex wedge case. So what you're having here is a domain that starts this plate, and let's mark it with some other color to indicate that this is a plate, yes. And this plate is infinite, so but here we could always have a characteristic length L. The region, so for indicating the region that we are concerned with, we are using this L. So what you could write here is that, for example, you have something like u infinity right here. So the free stream velocity or the speed is u infinity. So due to the presence of a surface right here, this is the surface S. It the fluid layer that is close to the surface sticks in the sense that it does not slip over the surface. So what would happen that the velocity right here would be u equals to v equals to 0, since the fluid is entirely sticking on the surface. Let me write it as fluid sticks on the surface. Of course, this is assuming that you do not have some super hydrophobic phenomenon that does not allow the fluid to stick on the surface, and it just keeps slipping and rolling across, rolling along the flow direction. So assuming those types of things do not happen, what would happen is that u equals to v equals to 0 at the surface point, and let us mark these coordinates as y and this one as x. So at y equals to 0, the fluid sticks to the surface. So what would happen is that since this velocity is 0, and assuming a certain domain, let's say this one, let's call this domain, you see that the overall mass flow rate that is coming from this area, let's call this distance d. So you'd always have u infinity d would be equal to integral of u dy from 0 to d, right? Infinity d and ux. Let's call it at u at x, where x is something, some coordinates like this, okay? Now, you know, this ux must start from 0. Okay, ux with respect to y, if you plot this bars, this ux must be starting with 0, and it could be going somewhere above till u infinity. We do not know the profile. It could be this, it could be this, or whatever. We don't care at the moment. So yes, so in effect, we know that it starts from 0 and rises till u infinity. So what would happen that since the velocity starts from 0 right here, and rises gradually. So effectively, you'd have to extend this domain right along this to equalize the mass flow rate. So effectively, you'd be, since we are assuming that u infinity is here, so till for this part of, this part of the domain, you have the velocity u infinity. So the integral would be u infinity, and assuming that this is delta, that is the thickness of the boundary layer, the integral would be u infinity times d minus delta. And here you'd be having some kind of variation in u, uy, u as a function of y, and you'd be integrating uy dy from 0 to delta. So both of these combined would be equal to the mass flow rate, would obviously not be equal to the mass flow rate. So there is some certain deficit in the mass that is entering. Okay. Now that is the core concept of the boundary layer. So we are trying to obtain this mass deficit. So how to do that is that first we write the continuity equation, del x plus del v by del y would be equal to 0 for an incompressible fluid. And the momentum equation, x momentum equation, you could always write it something like u del u over del x plus v del u over del y would be equal to nu times del 2u over del y squared plus, yes, so this much is enough, I guess. Okay, so we maybe we won't be discussing how we arrive at this, or we could do that real quick, Yeah, we could do that. Let's say that the original Navier-Stokes that you have is, or we could change the color. I guess we could do that, yes. Let's pick out red. The original Navier-Stokes equations that you had in the x direction would be equal to minus 1 by rho dp over dx plus nu times, you have del 2u over del x squared plus del 2u over del y squared. This is how the equation looks, right? Now, okay, so then we probably have to go into a very detailed discussion of everything that's going on here. So I'm not sure what to do at this point. So should we take up that discussion or not? Well, yes, of course. I guess we need to take it up. Del v by del x plus v times del v over del y would be 2 minus 1 by rho dp over dy. You keep it as a gradient right here. Del p over del y plus nu times del 2v over del x squared plus del 2v over del y squared. Okay, from the momentum equation, you have u is of the order of u infinity, and not from the momentum equation, but from just observation. And from the continuity equation, you have this one. This is u infinity. This is L, your characteristic length. Let's keep it as v, and this is delta. So v is of the order of, delta u naught over L. Okay, so delta by L is much less than 1, so that implies that v is much less than u. So in this sense, you could always, ignore all these inertial terms and everything from here. So once you do that, you'd have something like del P over del Y is approximately 0. So if this is the case, then P is effectively Px, a pure function of x. Okay. So if the pressure is not varying along the y direction, we are considering that the pressure variations in the y direction are really insignificant compared to the pressure variations in the x direction. So what you could always say, since for y greater than delta, you have an inviscid flow. We could see this right here, right? That the boundary layer effects, the viscous effects are negligible after y equals to delta. So if you know this, or if you assume this, then you could always write that for an inviscid fluid, you'd always have P plus 1 over rho u squared would be equal to 0, since we are assuming a same plane, z equals to constant, would be equal to constant, not 0. So you could always write something like this, dp over dx plus rho. And since this is, the free stream velocity, you could always write it as u infinity du infinity over dx, assuming all the variations with y are insignificant compared to x, would be equal to 0. So this implies that minus 1 over rho dp over dx is equal to u infinity du infinity over dx. So if u infinity is 0, is constant, this would imply that dp over dx is 0. So this analysis can be extended to obtain, into this part. And on the right-hand side, you'd be having the scale is u infinity by L squared, and this scale is u infinity by del squared. So of course, this term would be much less than this term. So we can obviously neglect this. So, and this is anyway 0. So here you go. You get this equation. Okay. Yeah. So, and what are the boundary conditions? You have u at x comma y at 0 would be equal to 0. You have u at x comma y greater than delta is equal to u infinity. Greater than or equal to delta. So u at x comma delta is also u infinity. Is approximately u infinity. It's not exactly maybe u infinity. It is something like 0.99 times of u infinity. But we'll ignore those variations at the moment, for ease of calculations, of course. Okay. Just give me a moment. Okay, so let's start our process. Del u by del x plus del v by del y would be equal to 0. Now, and the other equation is u del u over del x plus v del u over del y is equal to nu times del 2u over del y squared. Now, from this equation, you could always do something like del u over del x multiplied by dy plus del v over del y times dy integrated with respect to within the boundary layer. So what we are essentially trying to do is find out, some things about the boundary layer. We are trying to obtain the momentum deficit, and we are trying to do certain things would be equal to 0. Since this is identical, since the RHS is identically equal to 0, no matter what you integrate it with respect to, it will always yield 0. And this would be integration of del u over del x times dy integral from 0 to delta plus this thing becomes v at delta minus v at 0 is equal to 0. Okay, yeah, give me a moment, please. Yes. Okay, so we already know that this would be something like 0, and moreover, you'd have yes, so you'd have del u over del x dy integral from 0 to delta would be equal to minus of v delta. The value of the vertical, that is the y velocity, at y equals to delta. Okay. So what you could always write is something like, we'd like to, have this as, you could write del y del x of u dy integral 0 to delta is equal to, we'd be using the Leibniz rule right here. Okay, so we'd assume that basically you could always write it as, you could find it out in any standard mathematical textbook. Thing like del over del x integral of 0 to delta u dy minus something. Okay, so let me just tell you briefly what it's all about. So for example, if you want to integrate something like this, differentiate something like this, which is a function of x and y dy. Okay. So what you do is you'd have to use the Leibniz rule, since this is also a function of x. So imagine this entire thing being integrated would imply that you'd have a certain you'd have no y right here. You'd have all would be delta del x. So what you do is that you'd first let's say this entire thing becomes something like this big U x comma delta as a function of x and delta. Or we could be a bit more general. Let's call this del 1x. So just yes, del 1 comma del 2. This would be how it looks like, right? And you have del over del x right here. Then you always know that this original function is just substituting del 1 and del 2 instead of the y terms that you're getting after integration. So of course, if you differentiate it again, there would be an extra del over del x term, but you can always revert back to the integrand of this particular integral. So knowing that, you could always write this as something like x comma delta 2 d del 2 over dx minus ux comma del 1 d del 1 over dx. Yes, and this would be the integral part, and there would be a certain other thing that you'd have to take care of, and that would be, this is all right, based on limits you have already completed this. And another part would be something that adds up right here. You'd have to add the increment del 1 to del 2, and you'd have del u over del x dy. Anyway, you can have all this in any mathematical textbook. So here you have del 1 equals to 0. So what you could write it, and what you need is this. You need this. So you could always write 0 to delta, del u over del x dy would be equal to u times x comma delta d del over dx minus del over del x integral 0 to delta u x comma y dy. So this is how it looks. Okay. So let me check if we have, so that we have not committed any error over here. And this is minus here. So once you need this part, you could always have this entire thing going to the left hand side right here, or as they should be fine. I guess, yeah. So we did a bit of a mistake here. This is right. Okay, so inserting this into the above equation, we from this part as u x comma delta d delta over dx. And ux comma delta is always obviously u infinity. So what you get from here is, and this is minus v delta. What you get from here is del over del x times integral u to delta u dy minus, could be right, del over del x u infinity delta would be equal to minus v delta. And this can further be written as del over del x integral 0 to infinity u dy minus integral 0 to infinity u infinity dy. Yeah, because this u infinity comes out and this entire thing becomes delta, would be equal to minus v delta. And this becomes my del over del x integral 0 to delta u infinity minus u times dy would be equal to v delta. So this is the first core equation of our study, where we are actively relating delta with u and u infinity. Next, let us pick up the momentum equation. So you might not notice it, but this thing can be actually written something like this. You have this plus v del u over del y. You see del u over del x here, you see del u over del y here, you do not see del v over del y here. So what we do is we add this term, these two terms right here. So since from the continuity equation, we already know this is already 0. So it does not matter what we add or subtract. If it is the addition, the sum of both of these terms, it will always be 0. But what would happen is you do it like this, you do one u here. So what it yields is a really interesting thing. You have del u over del x right here, plus you have got v del u over del y plus u del v over del y, which is equal to nu times del 2u over del y squared. And this, what is this? This is del y del x of u squared. It's easy to notice this, right? And this is del y of uv. Look how beautiful this technique is. Using one equation, you can transform the other equation into a completely into a form that is completely much better readable. What we do is we integrate everything with respect to dy from 0 to delta plus del over del y uv times dy from 0 to delta would be equal to nu del 2u or del y squared dy, again from 0 to delta. So this becomes, using the identical Leibniz rule. So how do you write this? this would become something like this. Keep this outside. U squared dy from 0 to delta minus ux comma delta, and this entire thing's square, and you'd have one term that is the first derivative of the upper limit, that is delta, and this becomes uv delta minus uv 0, of course this entire things, and this is actually del over del y of del u over del y. So this thing also is easy to write. This is del u over del y at delta minus del u over del y at y equals to 0. And this is u infinity. So you can always write it like this, del by del x, delta u square dy minus, you can always write it something like this, u infinity squared delta. Plus, yes, this one. Now, you notice this, that u and v at 0 is equal to 0. So this part is 0. And here you have at y equals to delta, u is u infinity. And you can always write v at delta as v delta would be equal to nu times. Now, interestingly, this thing, now I'll have to take up another analysis section. You know that tau x y would be equal to minus of mu, that is the dynamic viscosity of the fluid, del u over del x plus del v over del y. Right? No, not right. Wait, I'll have to clear it off. Yes, del u over del y plus del v over del x. So we already know this from the derivations of the Navier-Stokes equations. And okay. So yes, so we already know that v is of the order of u infinity del over L. So del v over del x is of the order of u infinity del over L squared. And del u over del y is of the order of u infinity by del. So multiply both sides by delta. This is u infinity delta over delta square, and this is u infinity delta over L square. So this term is much, much greater than this term. So this term can be conveniently neglected. So tau xy would effectively be minus mu del u over del y. Okay. Now, just consider this boundary layer. This is delta. Outside this, we assume the inviscid flow domain. Okay, and in inviscid flow, we assume the effects of viscosity have vanished. That would imply that tau xy for y greater than delta is 0. So this would imply that del u over del y at y greater than delta is also 0. And that's exactly what's written here. Right? So effectively, the equation becomes nu times minus del u over del y at y equals to 0. And this is minus 1 over rho times mu del u over del y at y equals to 0. And this is 1 over rho tau wall. Let's call this tau wall at the moment. The shear stress, xy shear stress at the wall. Okay, so what this gives us is something like this. Del over del x integral 0 to delta u square dy minus u infinity squared dy integral from 0 to delta plus u infinity. V delta can be obtained from this part. That is the deficit. Del over del x integral 0 to delta u infinity minus u times dy. And you have one extra u infinity right here. So you obviously need to square it up. And this is equal to tau all over rho. Everything right here becomes something like this. 0 to infinity, 0 to delta u squared minus u infinity squared dy plus del over del x, 0 to delta. Okay, so this is not 2. Let's just remove it in its all its entirety. That's why if there is at least someone in the live session who can point out these small little errors, it would always be good. Anyway, so since we don't talk about that. U infinity square minus u times u infinity dy would be equal to tau wall over rho. And this is equal to del over del x integral 0 to delta u squared minus u infinity squared plus u infinity squared minus u times u infinity times dy would be equal to tau all over rho. And this becomes del over del x integral 0 to delta u squared minus u infinity dy equal to tau all over rho. And if you solve this further, you always can get 0 to delta. Take u infinity squared common. This becomes u by u infinity squared minus u by u infinity dy. So this again becomes we already know, that all in this equation, whatever y terms you have, all of them would be replaced by delta. And delta is a pure function of x. So effectively, this entire integral would be a function of x. So so this partial term would be converted into an ordinary term. ordinary derivative, of course, and u by u infinity squared minus u over u infinity dy would be equal to tau wall over rho u infinity squared. So this is the second core equation that we have in our integral momentum analysis. Now you could also have, let's say for this, we need a certain u infinity times of fy, a certain formulation like this. Now, what people usually do is that they consider u infinity times, C1 plus C2 plus C3. Wait, not as easy as this. C1 plus C2y plus C3y squared plus C4y cubed. All right. So for this type of profile, what we need to do is, firstly, we need to understand that u at y equals to 0 is 0. This would imply that C1 is 0. Okay. And the second thing we need to realize is that u at y equals to delta is u infinity. So C2 delta plus C3 del squared plus C4 delta to the power 4, delta to the power 3. 1. That is another thing that we need to realize. And there are basically 4 constants. So we have du over dy at y equals to delta. This would also be 0 due to the shear stress condition inside the inviscid fluid. The shear stress in the fluid is 0. So leveraging that fact, we have here as C2 plus 2C3y plus 3C4y squared at delta is equal to 0. So C2 plus 2C3 delta plus 3C4 del squared would be equal to 0. Okay. One interesting thing is that outside the boundary layer, if this is delta, and for y greater than delta, tau, let's say this is tau 1, this is tau 2. Tau 2 equals to tau 1 equals to 0. This implies that du over dy is identically equal to 0 for y greater than delta. And if this is the case, for all y greater than delta, then you could always have, you'll also have dy squared is equal to 0 at y equals to delta, right? So then you would be having d2u over dy squared is also 0 at y equals to delta. This would imply 2c3 plus 6c4 delta is 0. This would imply that c3 is minus 3c4 delta. Put this right here. You will get c2 minus 6c4 delta square plus 3c4 delta square is equal to 0. This is the first thing. So you get c2 equals to 3c4 del squared. And again, you put this c2 into the original equation with the constants. So you could always have 3c4 delta cubed. And c3 is minus 3c4 delta. This would be minus 3c4 delta cubed plus c4 delta cubed is 1. Which implies that c4 is 1 over delta cubed. X not equals to 0, because at x equals to 0, you'd be having delta as 0. So this little delta cannot be 0 in this case. So c4 is this, and c3 is minus 3 over delta cubed times delta. This is minus 3 del by del squared. And c2 is 3 by delta. Three by delta, yes. So u becomes c1 is 0, c2 is 3 times y over delta. Plus c2 becomes c2 is 3 by delta. No, wait, that's already done. So we take c3. c3 is minus 3 over delta squared and y squared. Plus you have c4, that is 1 by delta cube, and you have y cube here. So, well, u at y equals to 0 is 0. And del u over del y at delta is also 0. Is it 0 right here? No, it's not, I think. Del u over del y at delta would be equal to 3 by delta minus 6 over delta square times delta plus 3 del square over delta cube. 3 by delta minus 3 plus delta. Yes, this works. And del 2u over del y squared at delta would be equal to 3 by delta is gone now. And this is minus 6 over delta squared plus this is 3y squared plus 6y squared by delta over delta cube. So this is also 0. Yes. Okay, so anyway, this profile works. Now, what you need to do is substitute this entire thing into this equation. Okay. U is U infinity times C1 is 0, C2 is 3y over delta minus 3 by delta 3y by delta squared plus y by delta cubed. Okay, so this is U. Now you need to substitute U as a function of U infinity right here and solve for all these things. So effectively what would happen is that the final result that you'd get, I'll just write the final result here. Okay, now you could also have this tau wall right here. You can write it like this, del y at y equals to 0. This is equal to minus mu U infinity. At y equals to 0, you have 3 by delta. And the rest of the terms are 0. So this is 3 mu U infinity over delta in the negative form. And minus of this entire thing. Perhaps, yes. Anyway, so whatever the calculations you can always perform here, those are not the focus of this class, but more is how you are obtaining this uh, integral form of equations, this one, and how whatever you are substituting inside this does not matter much. So most profiles that are reasonably accurate would give you a nice and decent answer. The thing is that you need to know how to, obtain uh, this part, because this is the origin for all different things that you could always play around with boundary layers. And in the end, you might just obtain something like this. So once you do this, you'd obtain something as a function of U you know, as a function of delta, something like maybe delta squared or delta, and multiplied by a certain constant term. That would be a number that you'd be obtaining by integrating y over delta dy from 0 to delta. So these type of terms. And so once you do everything, you could probably obtain something like this. There might be certain variations because of the profile that we have taken, but overall everything will look something like this. It would be equal to 3 times nu u infinity over 2 times delta. You can always check it out when you go back. And this is effectively an equation that allows us to integrate our system with respect to delta. So how do you do that? You just write del d delta would be equal to, you cross this out, 140 over 13 nu over u infinity, right? Dx, and integrate this. At 0, delta is 0, we know that because the boundary layer is just starting, and at x equals to x, delta is del x. So this becomes del squared over 2 would be equal to 140 over 13 nu by u infinity x. So del would be equal to square root of 280 over 13 nu by u infinity x. Or you could write delta over x is square root of 280 over 13, 1 over square root of u infinity x over nu. And this is equal to 280 over 13. Reynolds number in the form of x power 1 by 2. This is 4.64. Well, approximately, maybe. Re exponents 1 by 2. And similarly, you could always find out tau wall over half of rho u infinity squared. And you already know tau wall, right? So you could always have that. Anyway, so that was what I wanted to cover in the case of the boundary layer theory. And maybe in the next video, I'd be taking up one example on energy transfer. Energy transport, to be more precise. So let me write down the agenda for next class. Next class, yes. Mm-hmm. Okay. Energy transport. A bit about that. And we'd also have something like a viscous heat source generating heat based on viscosity. Okay, so it's not really complicated, but just, you need to read up a bit and understand what's going on. So I'd be uploading. So now we probably not have any live sessions. So what I'll do is I'll be uploading some videos that could help you in understanding these concepts better. So just check out the YouTube channel again. And that's it from my side for today. I hope you enjoyed this session. I'll be stopping the recording.